Okay, let's see how well they do. Hey X2. The designers of the Zig programming language have been working to find a suitable design for asynchronous code for some time. By the way, the fact that they're using asynchronous and not concurrent, it fills me with expectation. It fills me with expectation because it means that they have appreciated the distinction they were trying to make and the things that you unlock by making the distinction. I mean, that you unlock if you have an ecosystem that supports that kind of stuff. If you, like, for example, trying to make a distinction between async and concurrent in, I don't know, C#, it's not really gonna yield to any practical advantage for you because the ecosystem conflates the two concepts. So, but in our case, there's something to gain. Let's see. Zig is a carefully minimalistic language, and its initial design for asynchronous I/O did not fit well with its other features. So this is pointing to the 0.5 documentation. Okay. Now the project has announced. I mean, this point is. I would say that this sentence is slightly imprecise because there wasn't anything particularly wrong with the old async design, as in, well, it had the problem that it was conflating asynchrony and concurrency. So that was definitely a problem. But at the time, we didn't even know that you could make this distinction. So, anyway, but fair. Now the project has announced in a Zig Showtime video a new approach to asynchronous I/O that promises to solve the function coloring problem and allows writing code that will execute correctly using either synchronous or asynchronous I/O. Beautiful. In many languages, including Python, JavaScript, and Rust, asynchronous code uses special syntax. This can make it difficult to reuse code between synchronous and asynchronous parts of the program, introducing a number of headaches for library authors. Languages that don't make a syntactical distinction, such as Haskell, essentially solve the problem by making everything asynchronous, which typically requires the language runtime to bake in ideas about how programs are allowed to execute. Neither of those options was deemed suitable for Zig. Its designers wanted to find an approach that did not add too much complexity to the language and still permitted fine control over asynchronous operations, and it still made it relatively painless to actually write high-performance event-driven I/O. The new approach solves this by hiding asynchronous operations behind a new generic interface, I/O. If I wanted to be pedantic about terminology, I/O does not hide asynchronous operation behind a generic interface. It will hide non-blocking I/O. Like the I/O implementation will perform non-blocking I/O. Maybe it will. I guess it will do coroutine yielding if you're using an I/O implementation that uses coroutine yielding. It is not a generic interface. That is a good point. Although, you know, if you interpret the term generic as in generics, yes, you're totally right because it's a runtime polymorphic interface. But if you assume that generic is used to say, you know, like under a general interface that has multiple implementations, then yeah, that's fine. That said, no, it doesn't. I/O does not hide asynchronous operations. It's on you, the user of I/O, to use io.async. Like I/O itself, inside of itself, it doesn't call io.async. Or, well, that's technically not exactly true because, well, what it does is that it might call io.concurrent internally because to implement async, you can do try io.concurrent, otherwise run the function immediately. So some implementations do that, but tiny details like this aside, in general, async is something that you do as a user of the interface, not as an implementer of it. Anyway, any function that, by the way, all this stuff is minor. Like I'm being super pedantic, but so far so good. Any function that needs to perform an I/O operation will need to have access to an instance of the interface. Typically, that is provided by passing the instance to the function as a parameter, similar to Zig's allocator interface for memory allocation. Yep. The standard library will include two built-in implementations of the interface, io.threaded and io.evented. Yes. The former uses synchronous operations except where explicitly asked to run things in parallel. With a special function see below, in which case it uses threads. Okay, I think this is a bit imprecise, but I think this is still pointing in the right direction. So the reason, so here's what a literal reading of this tells me. That io.threaded will not do any form of concurrency except when you use io.concurrent. That is not exactly true. It will do things concurrently also if you call io.async. And also, parallelism is not a concept that you really observe at that level. So, again, let's learn together. Okay, so that we get used to these ideas. You need to hammer on the terminology so that by getting your terminology right, it takes you fewer brain cycles to reason about the concept. Parallelism is the property of a system where if doing task T, let's say task X takes T amount of time, when you're able to run multiple X operations in parallel, then it means that you can do N time X operations, and those will still take T time instead of taking N times T time, right? You'll do more than one thing in a total amount of time that is still the same amount of time that it would take you to do only one of these things. If that is the case, then you'll run those things in parallel. In a computer, CPU cores are an example of a unit of parallelism. The more CPU cores you have, the more things you can do in parallel. SIMD registers are an example of a unit of parallelism. A SIMD register allows you to have multiple instances of the data and run the same operation on all those multiple instances kind of all at once. There's some nuance there because, I don't know, it might be that you have a CPU where doing a simple scalar addition takes fewer cycles than doing a SIMD addition. But ultimately, if the SIMD addition instruction makes any sense, then it might still take more than one cycle, but it should take fewer cycles than if you were to just schedule all those additions one after another on the CPU. So long story short, the thing that they said with operation X run multiple times and T being the time that it takes to run the operation, I think you could still argue that it is parallelism, even if running N times the operation X, you don't get only T time, you get 1.2 times T. So like you have a price. There's extra overhead for this parallelism, but as long as you're getting a number that is lower than N times T, you're winning and you're running things in parallel, at least to some degree. There's other examples of parallelism. So there is parallelism that exists in the context of concurrency and threads and async IO. There's parallelism that doesn't play into that. So for example, SIMD is a type of parallelism that has very little to do with threads. There's also when you have like a hard drive and you're doing DMA, the CPU can tell the hard drive, please fill this range of memory with bytes from, I don't know, like these sectors, these offsets into your memory. And the hard drive can do that independently of the CPU. That is another source of parallelism because the CPU can do other stuff while the hard drive is busy doing that. In any case, so a very literal read of this might make you think that with the threaded implementation, only io.concurrent will do stuff concurrently. So let's mentally change this parallel to things concurrently. That is not true, but I still think that I'm still thinking that this would be explained better later on. Let's see. The latter, which is still a work in progress, uses an event loop and asynchronous I/O. They should be non-blocking I/O. You see how getting the terminology right really helps you understand things. And this is not horribly wrong, right? The whole idea is correct. It's just that by using these terms kind of interchangeably and not giving them their precise slot, you make everything more imprecise. Like stuff is slightly out of focus. So it uses non-blocking I/O. That is what we want to. This is the key distinction between io.threaded and io.evented. io.threaded uses blocking I/O. io.evented uses non-blocking I/O. io.threaded uses normal read-write syscalls, while io.evented will use io.o-ring on Linux. It will open sockets with the non-blocking flag. It will use KQ on macOS, etc. So nothing in the design prevents a Zig programmer from implementing their own version. However, so Zig's users retain their fine control over how the program executes. Yeah. Lawrence Crow, one of Zig's community organizers, wrote an explanation of the new behavior to justify the approach. Synchronous code is not much changed other than using the standard library functions. Sorry, let me reread that because I've been I lost focus. Synchronous code is not much changed other than using the standard library functions that have been moved under I/O, he explained. Correct. Functions like the example below, which don't involve explicit asynchronicity. Oh no, they're going for the other way of saying asynchrony. That's fine. Will continue to work. This example creates a file, sets the file to close at the end of the function, and then writes a buffer of data to the file. It uses Zig try keyboard to handle errors and defer to ensure the file is closed. The return type, bank void, indicates that it could return an error, but doesn't return any data. Correct. If this function is given an instance of io.threaded, it will create the file, write the data to it, and then close it using ordinary system calls. Correct. If it is given an instance of io.evented, it will use instead io.o-ring, KQ, or some other asynchronous non-blocking backend suitable to the target operating system. Correct. In doing so, it might pause the current execution and go work on a different asynchronous function. To be able to do so, the other thing needs to be concurrent. It's not asynchronous. Asynchronous is not enough. It needs to be concurrent because, okay, we mentioned that parallelism, CPU cores are the unit of parallelism. What is concurrency? Concurrency is the ability of a system to take a task, which we can simplify as being a function, execute it up to a point, pause execution, switch to another task, execute that one as well up to a point, pause it, and then return to the original task. That is concurrency. So in a computer, your unit of concurrency, the quintessential unit of concurrency are threads. And here's the interesting thing. Concurrency does not need parallelism. So if you have a single core computer, a single core CPU that supports multi-threading, you will still get concurrency. You will still be able to get concurrency because the CPU will be able to run a thread, pause it, switch to another thread, run it for a while, pause it, switch back to the original thread, and continue its execution. You will not get any parallelism advantage. So if you have concurrency, you can get parallelism out of concurrency, generally speaking. But you could say that if you can exploit concurrency to obtain parallelism, but it's not a hard dependency pretty much ever in order to be able to complete execution. So a single core computer that has multi-threading works fine. And what else? So yeah, so this idea of pausing execution and going to work on something else, that is concurrency. You're switching to another coroutine. Or you're switching to another coroutine for using a very like generic definition of coroutine. So you're switching to a different thread, you're switching to a different green thread, you're switching to another stackless coroutine, you're switching to another one of those, so between those things. And so an asynchronous function, like something that is asynchronous instead, is something that doesn't need to synchronize with the rest of the code. It's something that can be done independently, at least to some degree. So in any case, either way, the operation is guaranteed to be complete by the time write all returns. A library author writing a function that involves I/O doesn't need to care about which of these things the ultimate user of the library chooses to do. Yeah. Just got an oral I/O toothbrush. And on Twitch, nice. And people say that tailored advertisements are ineffective. Like, what better ad could you get than this one? Just think about it. Anyway. On the other hand, suppose that a program wanted to save two files. These operations could profitably be done in parallel. If a library author wanted to enable that, they could use the I/O interface's async function to express that it does not matter which order the two files are saved in. Yes. When using an io.threaded instance, the async function doesn't actually do anything asynchronously. It just runs the provided function right away. That is wrong. That is wrong. io.async will use multiple threads up to a limit. So it will use multiple threads. It will try to give you parallelism as long as it can, but it is not guaranteed to do so. If you run, like if for some reason you run out of resources necessary to spawn new threads, maybe you have an OS that puts hard limits on your program, and it only allows your program to spawn a second thread, and it will deny a third thread. Then what happens is that here we spawn a second thread to run this. Here we try to spawn a third thread to run this. We fail because the OS doesn't allow us to do that. And in that case, we just run save file immediately. So io.threaded will try to run things, let's say, at the same time as much as it can, because that's how you hopefully get parallelism. But it is not forced to do so. In case we run out of resources, then this runs immediately and everything is fine. So with that version of the interface, the function first saves file A and then file B. With an io.evented instance, the operations are actually asynchronous. Now, God damn it. You see how these terms actually do slot well once you understand the definitions that we use. So these functions are naturally asynchronous because one doesn't care about the other. They are always going to be asynchronous in that sense. So here, if you run it with io.event, you are running them concurrently. So first of all, this is not exactly precise with regards to how our stuff works. So there's a small imprecision in here. But most importantly, the operations are going to be concurrent. So they are in io.evented, they will run on two different coroutines. Or rather, even in this case, here, this is the key point of io.async. We will try to spawn a new green thread for each one of these guys, but maybe we run out of memory at some point, or we run out of some stuff, or like we hit some limit, at which point we will run the function immediately. So in both cases, that behavior is still going to be the same. All that said, it is more likely that you run out of threads than you run out of green threads, because usually, I don't know what the numbers are, but I think you can spawn like an order of magnitude more green threads than actual OS threads. Which, I mean, I think it's reasonable ultimately for it to be the case. And also, I will say this. My information might be outdated because I think this was definitely the case in the past. I don't know new OS developments, what they have, what they ended up, like if today it's actually, OS threads are actually much cheaper than in the past. You can spawn roughly 1,000 OS threads before you really screw yourself. Yeah, you can definitely spawn way more than those in green threads, for sure. Especially after we have like everything fully designed on our end in terms of sizing. The real advantage of this approach is that it turns asynchronous code into a performance optimization. The first version of the program or library can write normal straight line code. Later, if asynchronicity proves to be useful for performance, the author can come back and write it using asynchronous operations. If the ultimate user of the function has not enabled asynchronous execution, nothing changes. If they have, though, the function becomes faster transparently. Nothing about the function signature or how it interacts with the rest of the code base changes. Yes. One problem, however, is with programs where two parts are actually required to execute simultaneously for correctness. For example, suppose that a program wants to listen for connections on a port and simultaneously respond to user input. That is a good one, yes. In that scenario, it wouldn't be correct to wait for the connection and only ask for the user input. It wouldn't be correct to wait for a connection and only then ask for user input. Yes. For that use case, the IO interface provides a separate function, async concurrent, which we renamed to concurrent, that explicitly asks the provided function to be run in parallel. io.threaded uses a thread in a thread pool to accomplish this. io.evented treats it exactly the same as a normal call to async. This is the same misunderstanding from before that it's bleeding down. It's not exactly like this. Well, I'm not gonna annoy everybody about this because we already know how this works. But yeah, if the programmer uses async where they would have used async concurrent, this is a bug. Zig's new model does not and cannot prevent programmers from writing in correct mode, so there are still some subtleties to keep in mind when adapting existing code to use the new interface. The style of code that results from this design is a bit more verbose than languages that give asynchronous functions special syntax, but Andrew Kelly, creator of the language, said that it reads like standard idiomatic Zig code. In particular, he noted that this approach lets the programmer use all of Zig's typical control flow primitives, such as try and defer, and it doesn't introduce any new language features specific to asynchronous code. That is definitely correct. This is what Andrew has said. This is one of the goals of this design, and I mean, yeah, we don't have a special syntax for this stuff. It's just all userland because of that. And it is userland, and it also integrates reasonably well with try and defer. To demonstrate this, Andrew Kelly gave an example of using the new interface to implement asynchronous DNS resolution. I think that this was only demoed in at Zigtoberfest, I believe. I don't think this has been demoed before, so good job. The author of this post has also seen that, I believe. The standard get other info function for querying DNS information falls short because although it makes requests to multiple servers in parallel, it waits for all the queries to complete before returning an answer. Kelly's example, Zig code returns the first successful answer, canceling single L canceling. That is another interesting choice. What's funny is that asynchronicity, apparently it's not an English, like American English word, according to their dictionaries, but also but canceling with a single L is the most used form in American English. So pedantic. Yeah, I know. But you know why? It's because for me, canceling with a single L is so weird. I'm used to the idea of canceling with a strong L. So you want to double it. And when I read this, in my mind, it's like it's canceling, like in Zerglings or like Ziglings. I don't know. Anyway, another in-flight request. The other in-flight request. Okay. Asynchronous I/O in Zig is far from done, however. I.O.evented is still experimental and it doesn't have implementations for all supported operating systems yet. A third kind of IO, one that is compatible with WebAssembly, is planned, although as that issue details, implementing it depends on some other new language features. Yes, the original pull request for IO lists 24 planned follow-up items, most of which still need work. Still, the overall design of asynchronous code in Zig appears to be set. Zig has not yet had its 1.0 release because the community is still experimenting with the correct way to implement many features. Asynchronous IO was one of the larger remaining priorities, along with native code generation, which was also enabled by default for debug builds on some architectures this year. Zig seems to be steadily working its way towards a finished design, which should decrease the number of times Zig programmers are asked to rewrite their IO because the interface has changed again. What is this again link? Writergate. Yeah, it's fair. Okay, there is one misunderstanding with regards to the semantics of async, but I would say it's ultimately a minor one. I think it's big enough that it should warrant fixing, but it doesn't detract from the overall narrative, which has been definitely understood by the author. So I would say overall, good quality article. Again, not perfect, but I don't know. If anybody from that contributes to LWN is watching this, I would say consider reaching out when you're writing this stuff so that we can point out if there are errors. It's easier for us to find errors of this kind. Obviously, I know that that stuff like LWN wants to be able to write stuff that doesn't necessarily agree with our narrative. But in this case, it's it's really entirely like a technical misunderstanding on the semantics of one function. Anyway, good stuff.